Hello everyone, welcome to PRiME 2020 presentation number A01-0022. My name is Xueping Ong. I'm an associate professor at the University of California, San Diego. So today my talk will be on novel disordered Rocksalt electrodes for safe, fast charging lithium-ion batteries. Or to paraphrase a very famous talk on nanotechnology by Richard Feynman, there's plenty of room in the disordered Rocksalt. So as many of you may well know, today's symposium is in honor of one of the three winners of the Nobel Prize in Chemistry in 2019, Professor M. Stanley Whittingham. I actually got to know Stan only back in 2014 when after I became an assistant professor. So I was invited to join his Energy Frontier Research Center as a new member, as a new computational member. And just to say a few words about what Stan means to me, I always see Stan as my own personal Professor Miyagi, for those of you who have watched the Karate Kid before. So Stan has been in the lithium-ion battery research since the very, very beginning. Okay, so he has done lithium-ion battery research for the past 40 years, and he has continued to be active in lithium-ion battery research. So he has such a wealth of knowledge about lithium-ion battery chemistries that it is kind of frightening. All right. So I remember that frequently when we meet up during one of those DOE review meetings, I would excitedly go to him and tell him about this new lithium-ion battery technology or sodium-ion battery technology that I'm working on. And he would then proceed to tell me, oh, we actually tried that in the 1980s or 1990s. And these are all the problems that we found with this technology. So Stan is a very, very useful sanity check. Okay, so every time you think of that you have a new idea or you hear some hype about lithium-ion batteries, you can always go to him and he will tell you, well, this is nothing new, right? And it is always good to have that kind of check before you do your research. Okay, so today my talk is actually going to be on the anode for lithium-ion batteries. Now, many of you may well know that we do have anodes today, and we have two very, very imperfect solutions. Okay, on one hand, we have the anode that is the dominant one in most of the lithium-ion batteries that we use in commercial applications today, and that is graphite, right? So just to show you how old these anodes are, I've deliberately chosen the very, very early works demonstrating their application as anode, right? So graphite was basically proposed back in the 1990s, okay? And so this is actually work that was done by Professor Jeff Dunn, right? And the reason why graphite is such a good anode is basically because of its very, very low potential versus lithium plus, okay? What this means is that when you use graphite as an anode, you do not lose a lot of energy density, okay, relative to the lithium metal, okay? And so you can make very high energy density lithium-ion batteries using graphite anodes. Now, however, the low potential versus lithium plus is actually one of the part of the reason why graphite is limiting in other applications, okay? So when you cycle graphite too fast, you run the risk of lithium plating, all right? And that carries with it a significant safety risk. Graphite also experiences relatively large volume changes when you cycle it, okay? Again, contributing to cycling stability and safety, right? Now, graphite essentially is what is known as a high energy density but somewhat low rate material. Now, there is an alternative to graphite, and this is also this material was also discovered in the 1990s. Okay, so and that is the lithium titanate spinel. Okay, so while not as dominant as graphite, it is actually used in commercial applications in very high rate applications. Okay. Now, the reason why the lithium titanate spinel is a good anode material is because it is what is known as a zero strain material, right? So when you cycle the lithium titanate spinel, there's negligible volume change, and it is also you can also cycle it at extremely high rates, okay? And that makes this spinel anode very, very safe, right? Now, the problem with the spinel, of course, is that it has an average voltage of around 1.5 volt versus lithium plus. And what this means is that you lose a lot of energy density if you are using the lithium titanate spinel as the anode. Okay. Now, in recent years, the disordered rock salt materials have garnered increasing interest as potential electrodes for lithium-ion battery applications. Okay, so the disordered rock salts are actually not new, right? So even back in 1994, Delma actually showed us that if you lithiate the vanadium oxide V2O5, and you actually get this series of phase transformations, and eventually at around after you lithiate about 3 lithium per formula unit of V2O5, you basically you end up with what is known as the omega phase of Li3V2O5. Okay, and that phase actually has a disordered rock salt phase. Okay, and then you can continue to cycle this disordered rock salt phase by delithiating and lithiating it, right? Now, more recently, the electrochemical formation of disordered rock salts has been shown in other transition metal oxides. So, for example, there's this work that was done showing that you can also form disordered rock salts by lithiating Li2MnO4, right? Now, the reason why disordered rock salts are very, very interesting as very interesting as electron material is really due to this work by Gert Sieder in 2014, right? So in 2014, Jin-Hyu Lee, who from Gert Sieder's group, actually showed you that when you have a lithium excess disordered rock salt material, for example, Li1.2 Mn molychromium oxide, okay, you can actually charge and discharge you can charge and discharge this as a cathode with very, very large capacities, okay, close to 300 milliamp hours per gram, right? Now, even more importantly, they actually showed that the reason why you can achieve such large capacities in this lithium-rich disordered rock salts is really due to what is known as a percolating network of what is known as zero transition metal channels. Okay, so when you think about the rock salt, and there are these tetrahedral sites that your lithium actually has to hop through when you transition from one octahedral site to another. Okay, they show that basically if your tetrahedral site is surrounded by only lithium, the diffusion barriers are actually much lower than if you actually have at least one or even more transition metals surrounding that tetrahedral site. Now, so in order for you to actually have a percolating network of zero transition metal type channels, you actually need a certain threshold of lithium excess to achieve that percolating network. Okay. Now, what is surprising thus far is that since this work in 2014, so far no one has, to my knowledge, has actually proposed disordered rock salts as potential anode materials for lithium-ion batteries. Okay. Now, like like many scientific discoveries, there was actually a little bit of serendipity involved in the discovery of this anode material. Okay, so this was back in June 2018. So just to show you how long it took for us to actually get this book published. So my colleague, Professor Ping Liu, and his postdoc Hao Tong Liu from at UCSD decided to come to my office. Okay, they actually took that walk, very, very long walk from their office in the Center of Magnetic Recording Research, all the way back to my office in the Structure and Materials Engineering building. And they basically said that, well, we have some very interesting results on this material that we do not fully understand, okay? And we are hoping that you can do some calculations to help us understand it, right? So, so basically what they did was that they decided to revisit the result of Professor Delma, okay? So they took V2O5 and they tried to lithiate it. They go as they continue to lithiate it down to 1 volt, they essentially reproduce all the results that were reported by Delma back in 1994. Okay, you see all these phase transitions from alpha to epsilon to delta, all the way down to the formation of your Rocksalt gamma phase, right? Now, what they did that previous people never did was to really try to further lithiate it. Okay, so they continue to lithiate it all the way down to 0.01 volt, and to their surprise, they found that, oh, there's actually a significant quantity of capacity below 1 volt, right? And this is actually very surprising. Okay, so where does this additional capacity actually come from? Now, even more importantly, this additional capacity is actually very interesting for anode applications. Okay, what you notice is that this additional capacity actually occurs at an average voltage of about 0.5 to 0.6 volt versus lithium plus. Okay, so what this means is that it has a slightly higher voltage than your graphite anodes. Okay, which makes it less prone to lithium plating. Okay, but yet it is still much lower than your lithium titanate, which is 1.5 volt. And so it still has very high energy density, right? So so they actually confirmed that this is indeed the disordered rock salt using both XRD experiments as well as neutron diffraction. Okay, and they confirmed that essentially during this entire additional capacity that you see below 1 volt, you still have the rock salt phase. Okay, now today I'm going to focus primarily on the science behind this additional lithium intercalation into the disordered rock salt. Okay, so I'm not going to talk so much about the electrochemical performance and the experimental setups. Okay, except insofar as it pertains to the performance of the material as well as the computational results that I'm going to show. Okay, so I'm going to really focus on just what insights can we gain from this behavior, right? So let me start by showing something that is familiar to every one of you, okay, which is the disordered rock salt crystal structure, right? So I want to first establish a common language, okay? So this is our FCC oxygen lattice, okay? So this is the starting point of our disordered rock salt, right? Now, as anyone who has gone through your undergrad chemistry, we know that our FCC lattice has one octahedral site and two tetrahedral interstitial sites per oxygen, right? So basically, when you actually occupy all your octahedral sites, you basically have what is the your rock salt crystal structure, right? So so this is actually what is happening in Li3V2O5. Okay, so in Li3V2O5, you notice that you have a cation to anion ratio of 1:1. Okay, which is your rock salt, right? Now, so I actually prefer this notation, so I'm going to stick to this notation throughout the rest of my talk. Okay, so we can rewrite this as basically lithium 0.6, vanadium 0.4 in the octahedral site with one oxygen, right? And this gives me my disordered rock salt crystal structure. Now, so in Li3V2O5, you have a 60% of occupancy of lithium in our octahedral site and a 40% occupancy of vanadium in the octahedral site, right? Now, this is the starting point of our disordered rock salt, okay? Now, when you lithiate, okay, the obvious thing is that since all the octahedral sites are occupied, there are no other octahedral sites to go to occupy. Naturally, your lithium has to go into the tetrahedral sites, right? So, this I have deliberately colored this tetrahedral lithium different color just to distinguish it from our octahedral lithium sites. Okay. Now, during the cycling of the disordered rock salt Li3V2O5, Haotong and Ping were able to cycle it between Li3V2O5 and Li5V2O5. So, so we know that basically we can get it up to about lithium 1, okay? However, what we do not know is really what is the occupancy of lithium throughout this intercalation insertion lithium insertion process, right? Now I'm going to go to our my favorite tool for understanding the thermodynamics of lithium intercalation, which is the phase diagram. Okay, so what you see on this slide over here is the lithium vanadium oxygen phase diagram that I downloaded from the materials project. Okay, so this is the database of all the known materials that with all the computed energies, and we can construct this phase diagram from the 0K DFT energies. Okay, so let me first label the lithiation pathway for V2O5. Okay, so so if you start from V2O5 and you insert lithium into V2O5, this red line actually shows you the lithiation pathway. Okay, now between this shaded region over here is what I call the cathode region. Okay, so this is where Professor Delmar was operating. Okay, so when you lithiate V2O5 down to this composition over here, you basically get your Li3 V2O5, and if you cycle between Li3 V2O5 and V2O5, you basically get this. You're basically operating within this gray region. All right. So this is using DFT calculations. We basically computed different orderings for the disordered rock salt as you try to attempt to insert more and more lithium into Li3 V2O5. Okay, so let me now go through what our observations step by step. Okay, so at the start of lithiation, okay, so when x is equal to 0, we have Li3 V2O5. Okay, we are essentially at this yellow dot over here. Okay, and the Rocksalt formula, as I mentioned before, is Ls 0.6 V 0.40, right? Now, what we found was that when we first insert lithium into a tetrahedral site, the most favorable site for lithium insertion, unsurprisingly, is the zero transition metal tetrahedral site. Okay, so this has the lowest site energy for lithium insertion. Okay, this is the most favorable site. Okay, and this constitutes about 12% of all the tetrahedral sites in Li3 V2O5. Okay, now if we actually look at the one transition metal or even more than one transition metal tetrahedral sites, basically all the site energies are greater than 400, at least 400 MeV in energy higher. Okay, so so we are not going to think about all these sites. Okay, so those are really much more unfavorable than our zero transition metal tetrahedral sites. Okay, so as we continue to lithiate, okay, what we found was that when you insert this lithium into this tetrahedral site, what we observe is that due to electrostatics, okay, so we have each tetrahedral site is phase sharing with 4 other octahedral lithium. Basically, what happens is that your lithium in your neighboring octahedral then begins to displace a little bit. Okay, the displacement is about 0.2 to 0.3 angstroms. Okay, however, that displacement is still relatively small, so we still classify those lithium as being in tetrahedral in octahedral sites rather than some other coordination. Okay, so this accounts for what is happening in this entire region 1 of the intercalation process. Okay, you are basically inserting lithium into tetrahedral sites, which is why you see this increase in tetrahedral lithium occupancy, while your octahedral lithium occupancy still remains constant. Okay, so you have displacements of lithium, but the occupancy actually does not change, right? So this happens all the way up to about lithium 0.5 or so, lithium 3.5, V2O5 or so. Okay, now as you continue to lithiate, okay, what happens is that between lithium 3.5 and lithium 4 V2O5, you basically have the increased electrostatics from many lithium being inserted into the tetrahedral sites then begin to force some of the octahedral lithium into other tetrahedral sites. Okay, So this is why in this region 2, okay, you actually see that your octahedral lithium occupancy begins to decrease from 0.6, okay? Initially, the decrease is fairly gradual, while you are accompanied by still an increase in tetrahedral lithium occupancy. Okay, so now the lithium tetrahedral occupancy actually increases at a slightly faster rate. Okay, until you hit this lithium 4 V2O5 composition. Okay, now what we see at Li4 V2O5 at this composition is that you see a sudden complete rearrangement of lithium in the disordered rock salt crystal structure. Okay, you have this sudden drop in octahedral lithium occupancy, while you see this sudden jump in lithium tetrahedral lithium occupancy. Okay, and you can understand this from the phase diagram, right? If we look at where Li4V2O5 is, it's actually sitting on this tie line between Li2O and LiVO2, right? So in LiVO2, this is our standard layered crystal structure, which is essentially a rock salt, order rock salt with octahedral lithium and vanadium. And on the other end, you have Li2O, which is an order rock salt. Again, you can think of it as an order rock salt with just all the tetrahedral lithium occupied. Okay, so when you hit this Li4V2O5, essentially there's a sudden driving force for lithium to get into the tetrahedral site. In other words, it is trying to become more Li2O-like. Okay, and so basically your lithium occupancy in the octahedral site drops to about 0.1. Okay, your vanadium never changes. Okay, so your vanadium is always in the octahedral site. Okay, and now you starting from a much higher occupancy of lithium in the tetrahedral site. Okay, so this is a redistribution of lithium, right? Now, as we continue to lithiate from Li4V2O5 to Li5V2O5, basically all that happens now is that you are now increasingly inserting lithium into tetrahedral sites, and the occupancy in the octahedral sites no longer changes. Okay, and that is basically region 3 over here. Okay, and the endpoint, at least what has been experimentally achieved so far, is Li5V2O5, which you basically have 0.9 lithium in the tetrahedral site. You only have 0.1 lithium in the octahedral site and 0.4 vanadium in the octahedral sites. Okay. So this is basically the lithiation mechanism, right? Now, from the lithiation mechanism, we can then compute the energies and construct the convex hull, and then calculate our voltage profile. And this green dashed line essentially shows you the average voltage that we compute using the PBE plus U functional. All that I want to say here is that it is the average voltages are in fairly good agreement with what we actually get from with these experimental voltage curves that were measured by Ping Liu. Okay, now during the lithiation and the delithiation process, we also found that the volume expansion for this anode is actually fairly small. Okay, it's only up to about 5% or so, right? Now, I'm going to now switch gears a little bit to talk about the electrochemical performance of disordered rock salt Li3V2O5. Basically, these are just some of the experimental results that were from Professor Ping Liu. Okay, so this disordered rock salt anode is actually phenomenal. Okay, in terms of rate capability. Okay, so they tested this disordered rock salt insertion disordered rock salt anode at charging rates of between exciting rates of between 1 ampere per gram to 20 amperes per gram, which corresponds to about 2.6 hours to a 20-second charge of discharge time. And as you can see from this cycling curve, curves, the capacities are extremely stable. Okay. They also constructed a full cell using our NMC cathode together with this disordered rock salt Li3V2O5 anode. And again, they can show extremely stable cycling up to more than 1,000 cycles. Okay, so in short, the performance of this disordered Rocksalt anode is actually very, very good. Okay, the rate capability of this disordered Rocksalt is very good. Okay, so to answer why the electrochemical performance is so good, okay, so we actually perform Nash elastic band calculations to understand the diffusion kinetics in the disordered Rocksalt, okay, both at the start of charge and the start of discharge, okay. So let's start with first the Li 0.6 V4 V 0.40, which is our Li3 V205, okay. So just to remember, okay, at this starting composition, we have all the octahedral sites occupied, right? Now we are inserting lithium into a tetrahedral site, okay, when we first insert lithium, right? So there are a few potential diffusion pathways for lithium, okay? So you have one possible pathway is basically you have this lithium in the tetrahedral site and you just hop directly into our neighboring tetrahedral site, okay? Now this requires requires the lithium to pass through this H-shed lithium, okay, and also it passes through this this oxygen shed oxygen H is actually neighboring two fully occupied octahedrals. Okay. Now another mechanism that we investigated is this what is known as our TOT cooperative mechanism. Okay. In this mechanism, basically what happens is that we have lithium from this tetrahedral site going to this octahedral, but at the same time, this octahedral site then now lithium then now hops into one of the neighboring tetrahedral sites. Okay, so in other words, this is a two lithium process. You basically have both lithium moving at once. Okay, so at what we found was that essentially at least at x equals to 0, which is Li3 V205, that cooperative process in which you have two lithium moving together is actually has much lower diffusion barriers than our direct tetrahedral to tetrahedral hop. Okay, so the barriers for all the cooperative mechanisms are about 300 MeV or below. Okay, while for the direct tetrahedral hop, the the migration barriers for lithium is close to 800 to 900. Okay. Now, so basically, we found that you do have a very fast diffusion pathway at the Li3 V205 composition. Okay. What about at the end of the process? Okay, which is closer to Li2, Li5 V205. Okay, x equals 2. Now again, we still have our tetrahedral and octahedral sites. The difference is that at Li5 V205, only 50% of our octahedrals are occupied. Okay, remember at Li4 we have a sudden redistribution of lithium. Basically, what happens is that we have now only 50% occupied octahedrals, while we still have a lot of occupied tetrahedrals and a lot of unoccupied tetrahedrals. Okay, so again, we look at two possible mechanisms. One is to just do our direct T to T, okay, again, okay. The difference being now that this direct tetrahedral to tetrahedral hop is now no longer hopping between two occupied octahedrals, okay. The likelihood is that the two octahedrals are actually unoccupied, okay, because 50% of the octahedrals are unoccupied, right? Now, the other mechanism that we investigated is our standard layered diffusion process, okay, in reverse, okay? So we hop from our tetrahedral to the intermediate octahedral, then to another tetrahedral site, okay? Now, to our surprise is that at Li5 V205, what we have is actually that the direct tetrahedral to tetrahedral hop is actually much lower in barrier than our tetrahedral octahedral tetrahedral hopping process. Okay, and this is really because now we only have half occupied octahedrals, and that actually lowers the barrier for this tetrahedral to tetrahedral hop significantly. Okay. Now, so those results essentially show that we have fairly low, we have very low barrier lithium migration across at least both at the start of charge and discharge for this disordered rock salt lithium Li3V2O5 anode. Okay, and that explains why we are actually able to achieve such high rate capabilities in the disordered rock salt. Okay. Now, for the remainder of my talk, I'm going to provide some insights which were actually not discussed in our paper. Okay, so I'm going to talk a little bit about what are some of the, what I see as the ultimate insertion limit into the rock salt crystal structure. Okay, and I'm going to address this from two standpoints. Okay, first of all, is redox. Okay, so again, let me go back to a more simplified version of our lithium vanadium oxygen phase diagram. Okay, so we can first draw two contours in terms of our cation to anion ratio. Okay, remember when you occupy all the octahedrals, you have a cation to anion ratio of 1. When you occupy all the tetrahedrals, like in Li2O, you have a cation to anion ratio of 2, right? Now, I'm also going to draw here the vanadium 2 plus limit. Okay, so let us assume that we can only lithiate our vanadates up to vanadium 2 plus. Okay, so even though vanadium 1 plus is known, it is not a very common oxidation state. Okay, let's set vanadium 2 plus as our limit, right? So we can start from LiVO2. Okay, so this is our standard layered structure. Okay, and indeed Peter Bruce has actually shown that you can actually further lithiate into LiVO2 to Li2VO2. Okay, so to write this in the Rocksalt formula, this is Li 0.5 vanadium 0.50. Okay, and when you lithiate, you essentially follows this lithiation pathway up to this position over here. Now, when you lithiate into LiVO2, again, now you actually get a much lower voltage material. Okay, so Peter Bruce actually showed this in this publication in Nature Materials, that if you lithiate into VO2, your voltage is is below 0.5 volt. Okay, it's actually fairly close to graphite. Okay, however, the rate capability, the cyclic stability is not as good as the disordered rock salt Li3V2O5. Okay. Now, there's another lithium vanadate anode that people have investigated, and this is fairly recent in 2013, and that is Li3VO4. Okay, if you write this in the Rocksalt formula, this is lithium 0.75, vanadium 0.250. Okay, now this is actually not in the Rocksalt crystal structure. It is still a closed pack oxygen, but now all your lithium and vanadium are in tetrahedral sites, and you actually start at vanadium 5 plus. Okay, so and when you lithiate, you actually get this. You actually follow this pathway over here. Okay, up to our vanadium 2 plus limit. Now, what you notice about this anode is that the capacity is extremely large. Okay, it's actually beyond 300 milliamp hours per gram. However, now your voltage is actually increased. Your voltage is now closer to 1 volt and actually slightly above 1 volt. Okay. Now, where the disordered rock salt operates is actually in between these two anode materials that people have actually investigated. Okay, which is this 3 yellow dots over here. Okay, so so essentially, when you take our lithium vanadates, okay, if I generalize the formulas for all our lithium vanadium anodes, okay, you have a formula of Li1 minus X VXO. You can lithiate up to Li2 minus X VXO, which is our vanadium 2 plus limit. Okay, as your X decreases, which is when you move from this LiVO2 to Li3VO4, essentially what is happening is that your voltage actually goes up. Okay, because you are now increasing the oxidation state of your vanadium. Okay, however, your maximum capacity also goes up. Okay, because if you look at this, the length of this lithiation pathway is longer than this particular lithiation pathway. Okay, Now, in our disordered rock salt material, we are actually somewhere in between. We are operating at x equals to 0.4, okay? And our maximum capacity is Li 1.2, V 0.40, and we have already achieved close to Li, the maximum capacity based on this V2 plus limit is Li 1.2, V 0.40. Experimentally, what Professor Ping Liu has achieved is Li1, vanadium 0.40, okay? So why can't we actually achieve Li 1.2, V 0.40, okay? We do have some hypotheses as to the reasons why, and this is based on energetics, okay? So if we think about our disordered rock salt at the end of our insertion process, which is LFI 0.50, sorry, LFI V205, okay? Remember, our octahedral site is 40% occupied by vanadium 2 plus or 3 plus. It is 10% occupied by lithium plus and 50% occupied by vacancies, okay? So if we think about the octahedral local environment around each tetrahedral site, we can actually construct what the distribution of this octahedral site is going to be, this tetrahedral site is going to be, okay? So the probability that you have a certain number of vacancies, lithium and vanadium around a particular tetrahedral site is given by this multinomial distribution, okay? And if you actually plot it out, okay, so this is actually the graphical representation of these multinomial distributions for different combinations of number of vanadium vacancies, number of lithium, and number of vanadium, right? Now, just from a very simple electrostatics argument, we can argue that, well, it is more favorable for that tetrahedral site to be occupied if you have vacancies beside it, okay, as opposed to having lithium plus, okay, and of course, if you have vanadium, it is going to be the least favorable, okay, because vanadium is in either a 2 plus or 3 plus oxidation state, okay. And what we found was that if you occupy all the sites which has 2 or more vacancies and less than 2 vanadium, essentially what you achieve is basically a lithium tetrahedral occupancy of about 0.45, and that is exactly the lithiation limit that we have achieved experimentally, okay? Now, the other thing to understand is that disorder is actually key to achieving this limit, okay? So if you have a nice ordered rock salt, what happens is that it no longer follows this multinomial distribution of around each tetrahedral site, and the number of tetrahedral sites that you can occupy actually decreases, okay? All right, so to conclude, there are two important messages that I want to communicate through my talk. First, there's plenty of room in the disordered rock salt, okay? We can use a general formula of Li1 minus x Vxo. We know that we can lithiate up to about Li2 minus 2x Vxo, okay, in the disordered rock salt, okay? However, site energetics can prevent reaching the maximum Li1 minus x lithium per oxygen intercalation, okay, as I showed in my preceding slide, okay. The second thing that I want to communicate is that in this disordered rock salt, you have a very, very interesting redistributive lithium mechanisms, okay. When you start inserting additional lithium, initially you have a very simple increase in occupancy in the tetrahedral site, but at some point, the entire process, the entire lithium distribution redistributes between the octahedral and tetrahedral sites, and that redistributive process actually results in low voltage and rapid kinetics, okay? In other words, a very, very exciting fast charging anode that we believe holds great potential for commercial applications, okay? So if you are interested in finding more about this work, please feel free to download our our paper, which was just published in Nature a few weeks ago, okay? So finally, I want to acknowledge my collaborators Ping Liu and Haotong Liu for bringing this very, very interesting scientific problem to my attention, and for all the exciting work they have done on the experimental front. I also want to acknowledge my students, Zhou Zhu and Yiming Chen, who were the ones who carry out most of the calculations in this work. For our calculations, for our computational work, this work was funded by the Department of Energy, and our computing resources is actually provided by XE. Okay. I also want to acknowledge all our other collaborators. Okay, so this is a huge piece of work with many collaborators in UCSD, Oak Ridge National Lab, UC Irvine, and LBNL, and Brookhaven, and Argonne National Lab are involved in different aspects of the characterization. Okay. And with this, I thank you, and I am happy to answer more questions during the PRiME meeting. Thank you.